Wind and mathematics, they seem like completely unrelated topics. So tell us more about this, Shaylin.
Well, yeah, this is definitely one of my personal favorites. I love it so much because it's an example of an abstract, pure mathematical result, which is quite serious and requires some rather heavy machinery within pure mathematics, but yet it also has a very nice real-world application or realization. So I'll begin with an intuitive formulation of the problem. Imagine I had to give you a basketball and I tell you I'll pay you a very large amount of money, like R1,000,000, if you can just do something very simple, and that is to simultaneously induce wind at every point on the surface of the basketball. And if you do that, I'll pay you R1,000,000. What would you say?
So I just induce wind on this ball?
Yes, you induce wind at every point on the surface of the ball.
Well, that sounds easy, so I think I'll win the bet.
Yes, well, that does sound very simple and does sound like you will be successful, but the hairy ball theorem actually tells us that this is impossible. And let me begin with some motivation which will hopefully convince you that you'll actually lose the bet. So suppose we have a basketball like this here. A very simple object like this here, we're all familiar with it. Yeah, this is supposed to be a sphere actually. And we want to create or induce wind everywhere, at every point on the surface of this ball. And let's try to analyze what happens when we try to achieve this. So we'll just place a fan here.
A fan? What fan is this?
Just something that creates wind, so just an ordinary electric fan, or whatever means you can conceive that will create some wind vectors. So we've got another fan here, and we can place as many fans as we want. We can place these fans over the ball. Obviously, it's a three-dimensional object. And anyway, what happens as a result of these fans here, I can place another one here, is that we'll end up getting some winds moving like this here, and we'll also get winds moving towards the other side of the ball, which we can't see. So we've got winds moving in all these directions. And on this end right here, there's no fans. There's no fans on the left-hand side, so this is going to be a peaceful point here.
But we can place a fan there.
Yes, we can place a fan here, but this is a peaceful point. So let's observe what happens when we place a fan here. So we place a fan here and it blows some wind here. This point is no longer peaceful because this fan is blowing wind at that point. So this point is experiencing some wind. So that's no longer peaceful. But we must just bear in mind that we've already got these fans blowing in this direction. So what happens is there is a collision between these wind vectors. And this collision results in many different kinds of spirals and complicated shapes. And miraculously, another peaceful point will just manifest itself somewhere. We are not entirely sure where.
So will we always find one peaceful point?
Yes, well, the hairy ball theorem guarantees at least one. There are situations where there's exactly one peaceful point, so we can't mathematically guarantee more than that. So anyway, in the spirit of creating wind at every point, let's try to place another fan here. And again, as a result of this fan here, this point will no longer be peaceful. But because we've got these wind vectors already in existence, there's going to be even more collisions between these wind vectors. You've got winds from this end, winds from this end, and all kinds of weird and complicated shapes will arise. And out of these weird and complicated shapes, you'll find some spirals. And again, another peaceful point will just manifest itself somewhere here, for example. You'll find a peaceful point there. And this process keeps repeating itself. No matter how hard I try, no matter how many fans I place around this basketball, there will always be a peaceful point. And the moment I get rid of one peaceful point by placing a fan and by blowing wind, that wind will cause more crashes with the other winds, and another peaceful point will manifest itself. And this will just carry on infinitely.
So I will always lose the bet.
You'll always lose the bet, even if you purchase 100 fans, even if you purchase 1,000 fans, and you blow wind from all conceivable angles and directions. These crashes will just manifest these spirals and complex geometric curves, and from them a peaceful point will manifest itself. So as the folk at The Real Hustle say, if it sounds too good to be true, it probably is. So you're not going to be losing, I mean, you're not going to be winning that 1 million rand, and you'll always be losing.
For what other geometric objects does this property work for?
Well, it certainly works for the sphere to perhaps characterize all objects for which this works for. May not be extremely easy, but for example, a donut shape like this here, a torus, this property here will always fail. So just imagine a donut that we eat. Imagine one of those little rings that kids play with in the pool, for example. It is possible to induce wind at every point here. So this result actually speaks to the intrinsic geometric property which is possessed by the sphere. This isn't some obvious thing. This whole idea of fans is just an intuitive explanation for the fact that there's always at least one peaceful point on a sphere, no matter how hard we try. That argument wouldn't work for a torus. So the mathematics really makes intimate use of the geometry of a sphere. And in order to prove this result, it's actually not easy at all. We don't just sit back and observe winds. We have to make extremely sophisticated use of algebraic topology. So this is why I'm so fond of this result. We can actually formulate it in a very rigorous way, and it's called the hairy-ball theorem. And it starts off with a continuous tangent vector field defined in the sphere. So we begin, if F is a map from S2 to R3, is continuous, and in addition to the continuity, I want to consider surface winds. So you'll recall that I mentioned I want to induce surface wind everywhere. So I'm not interested in winds which are going up from the surface to higher atmosphere, nor am I interested in winds which come down to the surface. So I need to just mention that this is a tangent vector field. So for every x inside S squared, if I look at f of x and I touch the initial point of that vector at x and I go to the terminal point, what I get is something which lies very nice in a flush, flat way on the tangent plane. So I'm not considering things like this here, and I'm not considering things like this here, I'm only considering tangents. So that line segment must be a subset of the tangent plane. Then what the hairy-ball theorem guarantees is that there exists a point inside S squared such that f of y is the 3 tuple 0, 0, 0, and this y is that peaceful point here. We're not sure where the y is. It will depend on the nature of your vector field. Initially our point y, which was stationary or peaceful, was this one here. But the moment you place a fan here, this was no longer peaceful. But then, because of the crashing of the winds, all kinds of whirlpools and spirals took place, so the y moved here. So this y is a moving point, but what we know is that at every moment in time, there is at least one y for which is completely peaceful, even if you place 100,000 fans and you blow wind towards it. So it's quite spectacular that you cannot induce wind at every point. And again, this result is purely logical. It makes no use of experiments, and this is what makes pure mathematics so very strong. Unlike any other science, this is a completely logical thing which isn't dependent on observations or instruments or scientific experiments. It's purely based on logic. And what this means is that no matter how bad the natural disasters get on planet Earth, you'll always have at least one peaceful point. We'll never have a day where it's windy everywhere. There's always at least one point for which there's absolutely no wind. And we know this with complete certainty, thanks to pure mathematics. And it's something that is to do with the intrinsic geometric property of the sphere. unlike the donut shape, for which this actually doesn't work. So yeah, that's just one of the ways that we can use pure mathematics to understand the world around us.